Is this thing on? Oh, I'm sorry. Excuse me. I was just having my morning snack. Today, what I wanted to talk to you about was covalent bonds and the energy involved in making and breaking bonds. The first thing we'll do is we'll consider why atoms bond in the first place, and we'll consider bond length, how far apart two separate atoms are, and we'll calculate the energy given off or absorbed when chemicals bond, and we'll talk about how we do our calorimetry experiment. Formation of covalent bonds and energy. The first concept is this: bonds form to lower the energy of a system. So if you look over here at this graph on the right, you can see that potential energy is on the y-axis. So these atoms have high potential energy. These atoms over here have high potential energy, but these ones have low potential energy. And basic fundamental concept in chemistry is things like to have low potential energy. And so this is the most likely scenario for atom A and atom B to bond together because they have low potential energy. The second concept is this: attraction and repulsion cancel to form a bond at a length where the potential energy is at minimum. So again, we'll visit this graph over on the right. It's kind of like the three bears. These two atoms up here are too close together. These atoms over on the right are too far apart. But these atoms are just the right distance apart. The third concept is this: bonds have a particular amount of energy, and we can predict the amount of energy released or needed for a reaction to occur by using this equation. Delta E, or change in energy, is equal to the energy of the bonds broken minus the bonds formed. People have estimated the amount of energy found in different types of bonds. Hydrogen-hydrogen bonds have about 440 kilojoules per mole of energy. Oxygen-oxygen double bonds have about 500 kilojoules per mole. And OH bonds have about 460 kilojoules per mole of energy. If you look at the equation down below, we have two hydrogen molecules, the blue molecules, reacting with oxygen, O2, and they react to make two water molecules. All we have to do is figure out which bonds are being broken and which bonds are being formed. I guess logic tells us that these hydrogen-hydrogen bonds must be being broken along with the oxygen-oxygen bonds, and these bonds are formed. So if we use our equation and we calculate all the energy of the bonds that are broken, and we subtract the energy of the bonds that are made, the OH bonds that are made right here and here and here and here, and we add them all together, we should be able to calculate the amount of energy that is involved in this reaction. Either a positive or a negative number will result. We have a molecule on the left which is called propane, and that's going to react with 5 oxygen molecules to make 3 CO2s plus 4 water molecules. So we will be breaking 1, 2, 3, 4, 5, 6, 7, 8 CH bonds, so that's 8 times CH bonds worth 410, and we'll be breaking 5 times 500, and we'll add that up. We're on the right side of the bonds that we're going to build. We have 3 CO2s, so that would be O double bond C double bond L. So we'll break 1, 2, 3, 4, 5, 6. We'll break 6 CO double bonds. They're worth 805, or 6 times 805, and we'll figure out what that is. And we're also going to build 4 water molecules. Now each water molecule has 2 OH bonds, and we have 4 of them. I'm not going to draw them all right here. OH bonds are worth 460. So 8 times 410, 8 times 410 equals 3280. 5 times 500 is 2500. Total here is 80 and 7 and 5, 5780, and the total here is 4830, and 8 times 460, 8 times 460 equals 3680. 3680. All right, see if I can do my math here. 0, 1, 13, 15, 5, and 8. We're breaking 5,780 kilocalories worth of bonds, and we're building 8510. Now our formula was broken minus formed. So these are the ones that are broken minus formed. So the delta E is broken 5780 minus formed 8510 equals negative 2730. 2730 kilojoules per mole of molecules that are formed. So that's a negative number, and that means that energy would be given off in this chemical reaction. You might know the term exothermic. It would feel warm. Now there's another equation down below. This takes just a little bit more time because the first thing you need to do is figure out what the heck CH4 is. CH4 is a molecule that has carbon in the center and it has 4 hydrogens around it. H makes 1 bond and carbon likes to make 4 bonds. So that's what a CH4 is. Cl2 is a Cl bonded to another Cl. We're going to build H2, H bonded to H. We're going to build a CCl2H2, so it's a little bit difficult to know what this is. We'd have to look it up, but Cl, Cl, and then an H, and an H. We start off with these molecules, and we would have to break all of these bonds. CH bonds, 4 of them, a Cl-Cl bond, and we would build an H-H bond, and we would build a CH, 2 CH bonds, and 2 C-Cl bonds. And so we would just do the math like we did before. So the final thing today is this. Bond energy and calorimetry. What are some of the terms that we need to know before we do an experiment? Well, we're going to have an experiment in which we take some sort of food matter, something that sticks on a pin and burns easily and doesn't cause allergic reactions, probably not a peanut, even though peanuts are wonderful because they have a lot of energy. We'll take a food, we'll try and burn it, and we'll heat up some water, and when we catch the heat that's given off by the burning food item, we catch the heat in the water up here using a thermometer, would be in here. And if we know how much water is there, the amount of heat that's absorbed by the water is the same as the amount of heat that's given off by the peanut. The terms that you're going to need to know for this experiment will be temperature. What is temperature? It's actually the measurement of the kinetic energy or the movement of molecules. Heat is the energy transferred by a difference in temperature. So if it's hotter down here by the burning peanut and it's cooler up here, heat will be transferred to the cooler entity. Specific heat, well, some things heat up and cool down more quickly than others. For example, you don't want a blanket that heats up and cools down very, very quickly. You want to stay at a nice comfortable temperature. So you want something with a high specific heat to make up a blanket. So there's 2 different calories. There's a little c calorie and the big C calorie. Little c calories are the real calories. They're the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. And by the way, once in a while we'll need to use joules in our calculation, and 1 calorie is equal to 4.18 joules. Calories are what chemists use. If you look at the back of a package or the side of a package and you look at the nutrition label, you'll see that they always spell calories with a capital C, because what that really means is kilocalories. I don't really know why that is, but when they say 230 calories with a big C, they really mean 230,000 little c calories. So today, what did we do? We first set the stage, thinking about how many calories are in various types of foods. We talked about bonds forming to lower the energy of the system, and we talked a little bit about the bond length and bond energy, and that was the main part of our lesson. We did a couple of calculations in which we took the amount of energy in the bonds that are broken minus the energy of the bonds that are formed, and we calculated that out. And then we got ready for the upcoming lab in which we try and figure out how many calories are found in food items. Thank you for listening today, and I hope this all made sense, but make sure you stop in if you have any questions. Bye.